So I'm Jean-Philippe Mallet, I'm from CNRS Strasbourg in France.
And the first talk is, the program is not fully correct, so the first talk is on the Snap Microwave Toolbox by Michael Fumelis from the University of Thessaloniki. You're on, Michael.
Yes. Hi again. So now I will show you some developments on the Snap microwave tool of ESA. In fact, I have joined the team quite recently today. The presentation was not prepared by me, and so I will try my best. Let's start. So I don't know how many of you have used Snap in the past. Can you raise your hands? Maybe it's nice. So all of you. So I'm not sure if I'll tell you more things than that you already know. So I'm using also Snap, and this is not only for academic educational purpose with the students, but we, as I showed in the previous session, we are using it operationally for snapping toolbox on JEP. So it's a powerful tool. I believe it's open source, which is great. So, as I said, it's one of the freely available open tools of ESA for performing several interferometric processing. Not only about, 1 second, apologies. Not only Sentinel-1, but it is a mixture of operation for Sentinel-1, 2, and 3, plus other missions, other third-party mission and other. So it is a suite of tools that you can use. The advantage is that it is scalable to run also notebooks for large data production. And it tries to include some cross-cutting edge operators. In my own development, we are also integrating it on cloud resources, and it performs quite stable. So right now we are at the base of 1 million downloads, over than 1 million downloads, and 10,000 registered users on the forum, which means there are people who are using it actually and trying to have answers to their needs. And you can see the cumulative downloads here for a different version of the tool. Either it is Windows, Linux, and so on. I think most of the people are using it. If you are using only for 2 pairs of images or 1 single pair of Sentinel-2, so on, you can still use it on your own PC. But definitely, if you go to a step of processing multiple time series and so on, I don't know that if a single PC or local server can deal with that. And anyway, so in June 2023, this tool was renovated. At the end of this year, we are expecting support of other ESA mission, but we will go to these details later on. And from the end of the next year, it will support also NISAR, biomass, and other time series tools, but I think there are a few slides for that later on. Just to introduce the actual developing team. So it's Brockman Consult in Germany, Skywatch in Canada, and there is CS in France and Romania. This is, of course, with the support of ESA. The Aristotle University of Thessaloniki is included in the project as more consultant. So Snap Desktop. So I'll show you different things inside Snap. I'm sure that many of you, since everyone was raising its hand, have seen things like that. It's the visualization capability. So you can not only visualize Earth observation data, but you can also visualize some auxiliary data, land cover maps, or digital elevation models, and so on. So, and based on this data, you can either generate RGB, different kind of RGB automatically, so the system recognizes what kind of mission you are and adapts all the generation of the code and recognition of of the tool, of the operator based on each mission. To be honest, I was processing also with other kind of software, but for instance, if you have an image and you don't know where the image is located, you just have a zip file in your PC. For me, it is a great tool. You put it inside, it gives you the geolocation of the footprint, and also there are other tools inside that, like the one here, which is kind of library. So if you launch it, it scans your entire PC, grabs all the Earth observation products inside your PC, lists them, and you can do searches on that, and you don't need to go to each subfolder. You can use this data and store them locally and so on. So this is great capability. I don't know how many of you are using the product library. And of course, you have also a bunch of tools for data analysis, profiling, histogram, comparing the spectrum of different images and so on. In terms of processing, there is a different way to execute an operator. I think, as also we are doing with the students, you go first with a simple operator in the GUI. So you just go, select some images, go step by step on some products. The disadvantage of this procedure is that you have stored on your local PC all the intermediate products. So you run an operator, you save it, you run another one as an input to this one that you had already, and so on. And this is causing like kind of especially when you are having to deal with a lot of time series, takes a lot of time. Another advantage for the data processing part is, especially when it comes to the Sentinel-1 product, is that it reads already the zip file. This is not, I haven't seen that in other kind of software, which means that you just drop the zip file inside the tool and start using the product. In all the other softwares that I have used, usually you have to unzip the file, which means that you have double size product in your PC and so on. Still, when you have one pair to do or a couple of images, it's fine. But when you have like 300 scenes, SLC, this is like really a problem. This is even saving time when you do the processing on platform infrastructure, because there someone needs to pay for the computational power, and this makes a huge difference. Then, apart from that, you have the idea of building a chain of tools, which is the graph builder. So instead of running each of the operators separately and save each time the product from here, you have this graph, what we call it, and you don't have intermediate products, and you go and you save the last one. Of course, you can put right in all intermediate products that you need, but this is a very important way to process without storing things on your PC, intermediate products. Then you can go from very simple graphs like that to a very complicated ones. Now, although this seems very sophisticated and wow, it can generate millions of things for you, I would not recommend to go directly like that. The idea is that if you do like split one image into 3 sub-swath and merge them in the same time, usually this causes delays in the execution. So what you would do, in principle, you will just go in one split, you will go in this one procedure for one sub-swath, and then you can execute again for different sub-swaths and so on. So there are different ways to execute a graph, and also you can execute it within the GUI interface, but you can have the graph and execute it in a Linux interface with GPT. So you can just use already processing chains like the graph and execute them, and this is in fact the way how we execute the snapping IFG on the JEP platform. Okay, again, we have this, I can go back. So here are a few examples from Sentinel-2, normalized water indexes. This is a hot topic right now in Greece, where we have severe floods in entire country. This is a nice mosaic over Ireland using 16 scenes. It is a composite of backscatter coherence. And we go now to the SAR functionalities. So more or less, I think that all the operators that you would need to execute SAR processing or in-SAR, the in-SAR processing are available within the toolbox. And this does not only apply for strip map data, but also for top SAR. So this is quite important. Another very important advantage of the tool is, and by the way, I'm not advertising because just to advertise, but it is something that if you have deal with processing, you will understand the problems. For instance, automatic DMs. If I decide right now to process on Morocco, I need to go to fetch the data of the DM over Morocco, stitch them, prepare them in the format of the specific software in order to use them. And I should do exactly the same for orbits, which means that I need to go to the repository, download the orbits, either they are precise or restituted orbits, and put them in my processing. Here, these two steps are fully automatic. So you can download multiple datasets, DM datasets automatically. It will recognize the area of your image. It will recognize the dates. It will download automatically from the repositories the orbits, the DMs, use them inside the processing and so on. Even if you decide later on to call some land cover products or whatever, there are also automatic way inside that you click and the land cover product comes for this specific area inside different kind of product. So, I mean, there are a lot of things which are easing the execution of the processing. Now, quite important is the integration of Snap with other software, which is the Pulsar Pro, to do some polarimetric analysis. The polarimetric analysis done, there are several operators inside Snap to do polarimetric analysis, but the more sophisticated one on Pulsar Pro, you can reach them because the two software talk to each other. Then there is this integration with stamps and P-rate, which means that you can prepare the interferograms for the time series analysis. And this is what we are doing on JEP. In fact, we are preparing all the processing, the interferograms. We are exporting them in stamps specific format, and then we are using them for post-processing. And there is some open source software that we developed also with Jose Manuel to automatically called Snap to Stamps. So it is a chain that uses all this operator of Snap to generate automatically all the interferograms. Also the export for P-rate, and SnapView, of course, to do the part of spatial unwrapping. These are the supported missions. So you see that there is a bunch of missions already available, and the asterisks are for supporting additional products inside these missions. So for instance, Spotlight mode was not supported on Cosmos SkyMed, I think it is now. And you have more or less all the recent missions are there, which is an important step since there is ESA behind and keeping updating the system. So this is the product model idea that will be, it is introduced and it will be updated in the future. So you can read all the products of all of these missions with specific readers, and then you have a bunch of writers to export the products in specific format depending on what you do later on with your spatial analysis and so on. This is an example of flattened backscatter, sigma 0 backscatter over the Alps. So you can see ascending, descending, you have compensated most of the topography, so it is quite straightforward for interpretation. Then soil moisture tools. To be honest, I haven't used this part in the past, but this is, the Canadians are very proactive on that. So I hope that you have the opportunity also to use soil moisture toolbox for that. Multi-temporal mapping of DNSAR. This is things which have now updated tutorials inside, and you can have a stack of SLC products from Sentinel-1, and you can have all the differential interferograms more or less automatically generated, so you can see how you lose coherence with as you increase the temporal separation from the reference image. Quite important is this multi-reference INSAR analysis, because in the past it was not supported. You could not use, you had only one master reference scene, and with all the secondary ones you could have the pairs, but you could not have the secondary 3 with secondary 8. Now you can control, of course, the time and the baseline parameters to do, you can also visually see that, and you can do this. My only comment to Isa, maybe you will find a problem, is that all these are stored in a single product, which means that if you have a very long time series, that would be quite a large file to handle. Still, it has some capabilities when you process specific datasets. And this is an example of multi-temporal analysis, multi-reference analysis with the interferograms and the corresponding coherence map. And you see that these products include inside several interferograms, several coherence, and so on. This is a Spotlight co-registration, so it is now available on Snap. I don't know if you see, due to the demulation procedure, you see you see here the bands, that kind of zonation that you see here. This is well taken care of. So in the past you could not use properly the Spotlight mode, but now you can co-register SLC from Spotlight mode as well. Ionospheric correction tool, this is quite important for some specific regions. So you have the original interferogram. You have, this is not, you cannot correct that with baseline refinement or other procedure, or you remove only the quadratic phase. If you have the capability with split band to extract the ionospheric phase, you can correct the interferogram for this kind of error sources. Yes, so the Pyrite workflow, I will not go to details, but just to tell you that inside now there is an orchestrator script. So all what you need to extract the inputs for Pyrite are already available in terms of script inside the tutorials available online. You have tools to decompose ascending and descending to vertical and horizontal east-west component. And now finishing with what we have right now. So this is the current situation. This is the current operators. And this is what we will have in March 2024. So we will have corrections for ETAD for both SLC and GRDs. We have improved co-registration based on the ETAD. Decomposition, spatial temporal analysis catalog stack, and several other classification algorithms. I am also new in that, so I'm looking forward to see all this development. What I would kindly ask from you is if you have some ideas or inputs for us regarding what could be beneficial for development, that would be really great to hear from you. So please come and see me, Marcus, Magda, or other people working on this development, because we can transform, we can add operators in an open source tool that everyone can use. Many thanks.
Thank you, Michael. Any questions?
It will be a polarimetric question? No. Okay. Not yet.
Hi. Thanks for the talk. I wanted to ask, and I realize this might be in terms of functionality kind of going backwards for most people who use Snap, but is there any plan to add into Snap, if you know, at any point in the future, image formation capability so that you could input level 0 raw data and go through image formation to SLC, doing things like autofocus and things like that?
You mean SAR processor?
Yeah, basically, yeah.
I don't know.
Well, I can comment that if there's an open source SAR focusing toolkit, we will gladly support it with Snap, but there's
Okay,
no
yeah.
development plan for that.
Okay, so, yeah. Thank you.
Now the question on polarimetry. No,
Yeah.
I'm joking. No, thanks a lot for your presentation. I just want more details on the update for SAOCOM. So which are the plans, especially to tackle the problems of the SAOCOM mission, like the top SAR, which is not really well really well done, and also if the tool will be able to make something on the irregular baseline that SAOCOM has. So which are the future plans, or especially for reading the data?
I think to put readers for the different products of SAOCOM, I think that's a priority. Once this is done, I think we need to check carefully which development needs. Also, you can comment.
Yeah, no, we are going to support the SAOCOM tops. I mean, it's a bit more complex than the standard reader. We're going to do it, but still the bursts are not synchronized, so it's not going to be the greatest mode for INSARs. And for the other things, I mean, do you have something specific in mind?
Not really, because we are starting also to work. We are working with polarimetry on SAOCOM, but I mean, this is in our cases because we have direct access to StreetMap, which is very easy in Argentina's. So I I will recommend to put the readers, for instance, in order to have access to this huge catalog provided by ASI, because at the moment, I mean, it's useless because there is no formal reader to have that. That is a strong recommendation I would...
Yeah, thank you, and I think you should also do it in the roundtable discussion at the end of the session. So let's...
Okay.
Yeah.
Yeah.
Thank you very much.
Hi, thank you for your talk.
Yeah.
Do you have any plan to support burst overlap interferometry for Sentinel-1 processing?
Sorry, can you repeat the question? So,
Do you have plan to support burst overlap interferometry for Sentinel-1?
we have no plans, but let's talk about it. It should not be too hard.
Thank you.
Okay, excellent. Okay, I propose to move to the next speaker. Okay,
Last question, maybe.
Yeah, the last one.
Hi, thank you for the talk. As we all know, Stamps was written for MATLAB, and so how does that work in your open access, open user sort of philosophy? And additionally, so has lots of particularly for the RAM, still available?
You talk about stamps, right?
Yes.
But stamps processing is not performed within the toolbox. So what you do, you are preparing the reference and all the other secondary image. You put them in a specific format, readable in directories for stamps, and then you just execute stamps in the MATLAB.
Yeah, and I can make a general comment about stamps and open source. So that's correct, it's not open source, you need MATLAB, but Pyrate is open source and it does SPAS. So that at least is the step to the open direction. I think we need to move on with the session. Okay. Thank you, Michael.
Thanks, Michael. Okay, so I introduce Giuseppe Santolanza from Direct Technology, and we will have a presentation about the data cubes for INSAR product.
Good afternoon. Yeah, thank you. Maybe some of you already heard about SAR2Cube project that ended in 2021, but I will focus more on the interferometric part. But I will have a quick look of all the projects. Okay, back in 2017, we participated to a SEOM project called SyncoMap to retrieve lane cover maps through multi-temporal interferometric coherence. We set up different data sets in all over Europe, and we retrieved these lane cover maps. But okay, but to do that, we have to store on disk more than 1,000 interferograms, coherent maps, differential phases, and also different kind of multi-look with different windows. So we starting to think that, back in 2017, a way to save space on disk. So what is the basic information we need to use these images with multi-temporal interferometry? So we did a new project called SAR2Cube that the main purpose was to prepare data and store in a platform, in infrastructure, to easy to access, fast, and then post-process with on-the-fly operator. So we did pre-processing based on Snap to register the images over a single reference image. Then we designed the infrastructure that based on Open Data Cube and OpenEO services. And then we developed a set of on-the-fly operator to access this data and process them, analyze them, and we did different kind of application. And most of them are already integrated in OpenEO platform. So here you can find more information about the project. And also the repository of the pre-processing and the Jupyter notebook of on-the-fly operator, and also the link to the OpenEO web editor. And
sorry about the technical problems.
No, no, è una indietro. Questa. Non so, lo spingo. Sì. Here, since the project ended in 2021, there is a list of already we participated to already in FRINGE 2021, iGuards Living Planet, and maybe some of you already heard about this in this presentation. Let's see a little bit what is the basic information we need to store in the data cube, in this SAR-Q2 cube, in this platform. And that is a set of register images to a single reference one. Then the geometrical phase component unwrapped that will be used later with on-the-fly operator for pick up a generic interferogram pair and compute the differential interferogram, and then a set of matrices to transform from slant range to geographic coordinates. So let's see, let's have an overview of the pre-processing based on Snap. Here, as you can see, you can find the link to the GitLab repository. So through an AOI, SLC product, we do the registration. And then I will, back in 2021, we did a workaround to retrieve the geometrical face component, but then we modify the code in Snap. So I will ask Michael maybe to do this update maybe in the next Snap to save the graphical face component that is the topographical and flat earth component. Say on this. Thank you. And then just, this is done just for the old data set, and then just one time the computation of geographical matrices for the conversion to slant range to geographical coordinates. And here in this link you can find the issue in the Snap forum we open, where it's detailed what we did to achieve this to store the topographical and flat earth component in Snap. So now we will compute interferogram and debarse it, and we will get already the bars flat earth component and topographic component unwrapped that can be used for differential interferometric purposes. Once we have the prepared data, we can ingest them in this structure based on Open Data Cube and also OpenEO services. Now we can find 6 different data sets that were processed in the framework of the second part of SyncoMap project that will be presented Thursday morning in the thematic mapping session. And you can access them and see what is stored in each data set. Okay. So once it's ingested, all the data set is ingested, we can access them to for different kind of application. We can access them through different kind of client, Python, based on Python, R, or JavaScript. And we can select different features of the data set, analyze them, and get some result. But also we can use the web editor of OpenEO platform to manage all the jobs we want to run and create graphs, execute them, and get the result we want. And use the already on-the-fly operator that are already implemented in OpenEO platform. So here I will go fast. We developed different kind of on-the-fly operator to temporal and spatial subset, compute intensity, amplitude, do some multi-look, boxcar filter, interferometry, pixel selection for PSI. There is not the full chain, but we stopped to the pixel selection. No, it doesn't go. And the geocoding process also. So I will tell you more about the interferometric part. So we pick up 2 different images. We compute interferogram. We combine the 2 geometrical components coming from the preprocessing. We remove from the interferogram. We compute the interferogram, and for each interferogram, we just need a complex product and a subtraction, so it can be easily parallelized with this on-the-fly operator. And then we also generated the mean coherence map, select pixel according to a threshold. See, sometimes it goes really well and another.
Yeah, you can do it.
When I do that, yeah, yeah. When I do that, thank you. So select pixel and then just without storing all the interferogram data set, just pick up the pixel we want and save the basic information about the pixel selection over the interferogram data set. So we just need to save a matrix number of interferograms for number of points. Here you can see the web editor of OpenEO platform, where we can draw the graphs. And here it's a complex graph, as you can see, for generation of one interferogram, but it's easier than the image. And here it's the here it's the result. And then here it's just a test we did with an 15 by 15 kilometer AOI. We compute 250 interferogram, differential interferograms. With 4 cores, it took 6 minutes, and with 1 core, just 20 minutes. With interferogram, differential interferogram, coherent maps, mean coherence, and selection of pixels. And here I give you some information on how to access the OpenEO platform and get free access to the dataset and test on your own the on-the-fly operator we developed. And just go through the link, filter by SAR2Q. You will get all the dataset we prepare for the SyncoMap project. And then you should ask these 2 guys, Michele Klaus or Alex Jacob from EURAC, to get the free access to the platform and check on your own. So this is, I think it's a powerful tool for the scientific community that can be used for free, and it's open to everybody. Thank you. And sorry for the inconvenience.
Okay. Any questions for Giuseppe?
Please wait for the microphone.
Thank you very much. It was not clear for me if you applied the atmospheric correction, and if
no,
so,
nothing of that. Just we we co-register the data, and we store in this structure, and then until now we can develop more tools on the fly to do that. So we are open to. Yeah. We are still working. So
yeah,
even
because
if
the results in that case, the results may not be so accurate as we wish. No.
This is just the basic interferogram dataset for the next step. Then we can correct the interferograms in a second step.
Okay, and one more. Who are the users of your platform?
Okay, I think OpenEO platform is quite known. I'm not the expert on this platform, but EURAC is really into this OpenEO platform that is, I think it's from Australia. and they are open to develop always new tools, and we are now step by step converting the developing we did in SAR2Cube available in open EO platform.
Okay.
Any other question? Okay, thank you very much, Giuseppe. So we move to the next presenter, José Manuel from REA. I mean, you will present an update of the Snap to Stamp library and software.
Thank you. Thank you, Philip. Welcome, everybody. My name is José Manuel, as already said. I'm going to present the evolution of the Snap to Stamps package, already mentioned a couple of times today. Well, probably, I don't know, let me ask, have you ever heard about this? Yes. You some yes? Okay. So otherwise I need to a bit more in detail. See this? How was it, Michele? No. And Mike? Yeah, okay. Cool. So let me be from here. Sure? No, yeah. Oh, okay, perfect. Yeah, that's good. That's good. You can try now. Maybe, yeah. Let me try. So what is it for? So some of you already know. So it's an open source package. It's based on Python wrapper. The version 1 was still old, so it was 2.7 based on Snap 6. So it was needed something else. And it was done to enable to have an open source DINSA processor to use with Sentinel-1 data when they come. So it was just done for fulfilling actually the need of the user community to do this kind of processing that it was not able to do with open source back by then. Yeah. So why version 2? As I said, it was already 5 years ago, so it needed a fresh update. So now it's based on Python 7, compatible with the Snap 9. And why we were doing that? Because obviously we have a lot of record on papers, research. It's being used also in courses, in trainings, online, webinars. So we thought it would be a good idea to give an update on that. So basically, obviously, during these last 5 years, there were a lot of people with different issues or suggestions or how to do this, or I need a specific different processing, or yeah. So we tried to improve it, to put all together. And it was obviously early this year, just before the deadline of the abstract, got contacted by Jonas, one of the authors, that he was he modified the original package to have it compatible to use with TerraSAX. So we thought it would be nice also to include and expand the list of supported sensors also with a workflow for TerraSAX stream map. And at the end, we wanted to make also things easier because the user community is quite large. Some of them are more experts, some of the ones don't. So we tried to make also easy the installation and the usage of this tool. So some of the features of the new release that happens actually this weekend, I just managed to publish it during the weekend. So as I said, it's based on Python 3.11, Snap 9, and then we have for single burst interferometry, it was before listening a question regarding something like that. We support external DMs, or we expanded the definition of the AOI is not only a bounded box or well-known text, also supports shapefile, KMZs, and GeoJSONs. We also provide some plotting, because before they were not providing any script to do the plot, so the user should look into it every time. And some other functionality for example, Sentinel-1 auto-download based on Alaska satellite facility. Why only based on Alaska? Because now all the Copernicus Sentinel data is evolving, so providing something that would expire tomorrow would make no sense. We will work on that maybe in the future. So this was the workflow that was doing the version 1. So you see, maybe you still remember that the master splitting was still based in opening the Snap GUI, selecting the OI. So now in the version 2, this is automatic as well. So also based in the gathering the feedback of some of the users to how to do this and how to do that. So we were expanding the capabilities, the functionalities, and as well the sensor supported. So you see now the right-hand side, you have all this similar workflow because it was based in the same package. But obviously the TerraSAR data is provided in different format, different things. So there were some adjustments that Jonas did himself, and we incorporated in the version 2. Yeah, it's quite simple. So as I said, in the original version 1, the minimum unit for interferometry was compatible with 2 bursts. So that was because we thought it was basically most of the cases will fit in there, but maybe people want really small area or wider area, right? So this version includes supports also the one single burst interferometry with the proper graphs, but also, yeah, with minimize actually the time if you do only that. But it also is compatible with merging subsword with different number of bursts, single burst with multiple, and so on and so forth. 3, the entire subsword, but obviously you need the resources for supporting this processing. Yeah, and the merging is done, well, the interferom is done still subsword by subsword, and then we have the merging before the stamps export. So here's a bit how it looked like, the new extended support for AOI definitions. So now we support all these kind of formats, which are many more, but we thought that these ones are already quite large list for the common ones used. And yeah, how it looks like now in this project.conf configuration file for which the package is based to get all the parameters. So you can, what is it, yes? No? Okay. So you have the mode, and depending on the mode, then the software reads either the definition of the coordinates or either the well-known text or the path where the AOI file will be found. So then, as well, for the plotting of the press data, we came into it because at the end it's always recommended to spend some time to see how the interference look like before doing through the entire PSI processing, because you don't know whether the resources were not enough and it was not, the entire interference was saved on this properly, there was no space or the resources or something happened. So it's better always to have a look at it in the interference before proceeding to the PSI, for which you will have another different amount of errors to solve, or APS, or whatever else to take care of. So, oh, went a bit through, right? Yeah. So this was it. Okay, yeah. Here I just put some slides just to show you all the different parameters that are now the list expanded a bit. But as I said, there are some of them that are based on the optimization of the disk and so on, the processing options. So you want to override, so you launch the same processing over the same project, but you have more images. If you don't want to overwrite, it will only process the new ones. Before it was processing the entire directory that was there, right? So now this will be avoided. You can have a smart disk, what I call it, that basically will remove or optimize all the different elements that they were repeated. It was the DM elevation band for each of the exported pairs, or you have also the master SLC for each of the exported pairs, but this one is always the same information. So in this case, we remove it from all the pairs that they are not only keeping only one, and basically creating soft links with the other ones. So the software thinks that their products are there entirely, so it's able to export it without any problems. Yeah, and then here as well for the auto, for the master or for the project itself, you can define which is the sensor, which is the polarization. Now we need the master folder, not the master file, because before it was only based on a single subsword, so it was pointing to the subsword that it was subsetted. Now, as your area of interest may have 1, 2, or 3 subswords, we just need the path to the folder where the master is saved. But actually, this one is the zip master image. It can be multiple master we will assemble, But yeah, for the rest, it's a bit modified with respect to the version 1. Then we have also the auto master selection. So here you can select whether you want to have the master the first image or the last image, or if you select manual, you may put there the number of the master sample you want to get. So the image number 10 or the image number 15. And as well, the last one, maybe it's a bit confusing, is just for the path to the external DM if you want to use any. Again, showing the AOI definition, but it's part of the project configuration file. And then in the right, also the Sentinel-1 auto-download that I incorporated here that is based in the ISF search package from ISF. So we based on that, but actually we kept the same parameters, but you can come here and just define what you want, and it will do the query and the downloading, but you need to have an active registered user on ISF. I'll put here the user, sorry, here, the user and password in the project configuration file. Okay, just the last thing, you need always to put where the snap installation folder, and now also where the home directory, the hidden one, which are the color palettes and so on. So we produce the interferons with colors and so on. So this is it. Okay. So now the installation, it is only these 4 steps. If you are using Ubuntu, for example, you have to install the dependencies of Snap, which are the libraries of FFTW and libgfortran to create the interferons properly. These operators need these 2 packages. Then you can download the GitHub of the package and create the conda environment, which actually this one is not only taking care of all the packages that are needed, but also includes a conda package I created myself of Sentinel-1 Toolbox version 9. So you don't need to download the snap anymore, the version 9, with the update of 9.02. So you can just really conda install, conda create this environment, and downloads the Sentinel-1 will be installed automatically as a conda package. So this, so people will not be confusing anymore if I'm using snap to stamps. I have a snap 8 or a snap 7, or we have a snap 10. So we will first, it will not be incompatible anymore. You will be able to have different versions, your own one and the snap to stamps snap installation. And then it will probably easy thing, so you have an error, it will not be based because it's incompatible. So this tool was tested with 3 different sites. 2 of them were with Sentinel-1 data, and 1 was with the TerraSerix data. Well, several gravity dams. So maybe Jonas may have more information if they're split in different data sets or one single one, but I think it was one single track. So, so it was tested end to end. So I did a snap to stamps approach and then also the PSI to see whether the results were something expected, because when using Snap 5, we found some issues that we reported to the developers. So that's why the first version that was compatible was Snap 6. So we did an end-to-end processing to verify that things were working, like pointer, thank you. So here, for example, one of the areas, the Abu Dhabi, which this morning I saw there was plenty of RFIs, indeed. Abu Dhabi and Dubai area is plenty of RFIs. So we use 25 free RFI data for, I think it was 2018-19, I think. And this is only 1 year, so don't try to take out any explanation of analysis what the deforming could be, because it's only 1 year data. And then for the, thank you, for the TerraSAR, well, we have a sample of the data, but still the PSI results, click again please, are not that yet because are going into publication of the author itself. So it's based on the PhD, so I hope that everything will go in the right direction. That. Please go next, yeah. So basically this is it, so there's not too much on that, but yeah, there's a nice update in which I believe it will be used as well as the version 1. Thank you very much.
Yes, thank you, Jose Manuel. I think we have plenty of time for questions.
Thank you very much for the presentation. My first question is if you are planning to adapt the software for SBUS. It will be great.
Yeah, it's only time-related things. If I may have time for that, yes. I have some requests in the queue for testing it, and I see today that Michael showed the multi-master selection working, so probably will be one of the candidates for the next release, yes.
Great. And also, a second question, in the last version, when you did the split step, the whole subswap was stored?
For the secondary images, yes.
Yeah, so
this
now,
still is the same here.
Yeah.
It is a bit large, but we ensure if you have any misalignment on the metadata of the products, that at the end the final product covers the area you wanted. Because we saw even with the testing of the and the passing of the years, with so many cases in which we try to use the same smart splitting for single bars or 2 bars, and in some cases you may find data that is not properly subsetted.
Okay.
So maybe metadata product or maybe something else related. So I prefer to keep the entire subswap split, so at the end the data gives you what you want. It's a bit more of hard disk resources and processing. Well, processing not too much, but these resources you need to have, yes.
Yeah, you can always change it in the graph file, no?
Yeah, sure. You can also change it. I prefer not to include it because otherwise could lead to these other errors. But I mean, it's just an update on the XML, yes.
Thank you very much.
Welcome.
Another question? Thank you very much, Mr. Manuel.
Okay. Yes. Just I would like to invite you, everybody, to test it. As now we have also the street map supported sensors. Take in mind that also not only Terasar, Cosmo, and all the other street map data should follow the same procedure. So maybe we could, I mean, it's an open source project. Everybody is welcome to contribute. The authors and contributor list is not closed, so please don't be shy and call us. Thank you.
Thank you very much. Okay, so no, I think it's Martin, I guess. Oh, sorry. Yeah, so the next speaker will be Martin Jussi from CGI, and you will your talk is about high-speed GPU INSA processing.
Good day, all of you. Good to see you. Let's see if this one works now. Yeah. I'm Martin from CGI Estonia. I'll tell you a bit about GPUs and SAR processing with GPUs. You will hear about a project background, the functionality of the software we've developed, some processing tools, examples, and performance, and some latest, newest developments and opportunities enabled. So I'll start with the GPU technology introduction. So you may have heard of the GPUs, but I'm not sure if all of you are really familiar with them. GPUs are a graphical processing unit, so traditionally the graphics card of your computer, which in the olden times used to be mainly used for video rendering or gaming. So anything really video related, like computer games or videos, we're using the GPUs. But in the contemporary world, they have been evolving a lot and getting much more of a generic use, especially really in the latest developments of the AI models have been kind of pushing the GPU development. So now they're used for AI model training. Also for cryptocurrency mining, that's a common use case, but the technology itself has become rather generic, so you could do various computational tasks that you could parallelize on the GPUs. So the idea of the GPUs, or really the benefit of the GPUs, is that you could do really massive parallelization of your code if your algorithm as such is parallelizable. What's that word? Yeah. So on a single GPU, you have hundreds or thousands of cores instead of a few, like 4 to 8 that a normal CPU would have. So the effect you get from GPUs is that if you parallelize your work, you get a very, very high acceleration. So there are some common languages or tools that are being used. So the most well-known technology is the NVIDIA CUDA,
which is supported on the NVIDIA GPUs, which you could find on most processing clusters nowadays. And there's also the OpenCL technology, which is open source, but I think it's a bit deprecating by now. So the performance trend is such, you may not see the labels on these figures too well, but what really matters is the essence of these figures and the graphs themselves. So the GPU performance has been advancing massively in the recent years. So the performance improvement over years is not really linear, it's exponential. So, which is not the case with the CPU technology. So CPUs, of course, are getting better as well, but there's really been a massive kind of a massive burst in the advancements of GPU technology in the recent years. And why it's so important is because of this. So you can kind of see the similar trends in the Earth observation data growth, and year over year you will have to cope with much more data. You will have applications that leverage different data sources, so somehow you would have to be able to process all this data that you're generating. So to tackle this problem, we have created a little software tool that we have called the ALUS toolbox. The ALUS, it's just a name, but you could think of it as maybe arithmetic logic units or something. So it's an open source tool set leveraging GPU technology to accelerate EO data processing. Today, we have also mostly been focusing on SAR, and our today's presentation is also focusing on SAR, because this is a SAR conference. But the toolbox is open source. You can go ahead, you can test it, you can give us feedback and ideas for improvements. Here's a link to the repository. On a later slide, I'll also have a QR code. So again, open source project, and is mainly developed throughout several ESA projects. So we've been very closely cooperating with FRINGE on this one, and it's either been under development or used for adding value in 5 different ESA activities nowadays. So from the very early start of the development of this toolbox, we took on kind of like a user-oriented approach. So we started consulting the SAR community to give us input on, essentially which algorithms are you using to do your work, and where are the processing bottlenecks? Which ones are the slowest ones you would like to get accelerated? And we based on our developments on that. So there are some names mentioned here. At least one of them is in this room. So there's been a quite diverse expert user community that we've been engaging, and we've got input from them. But they all seem to face pretty similar problems. So based on that input, we decided to develop a number of processing algorithms utilizing GPUs. We call these routines. And we've also been highly engaging with the Snap user community, and also we've actually been used, especially in the early days, we used the Snap toolbox as a kind of a reference implementation. So basically even like a kind of a ground reference data or a validation data for us. So we basically compared our results to the results from Snap, and moreover, we asked these expert users the questions like, okay, you do coherence, but show us the exact Snap functions that you're using and tell us which parameters you're changing, which ones you're not changing, which ones could be hard-coded, etc. So that gave us some ideas for the routines we want to develop. So we have a coherence estimation routine, a calibration routine, a more specific and a bit fancier timeline generation for coherence, and a generic resampling routine, which is not only applicable for SAR, but also for optical. And we have some SAR focusing things, which I'll tell you a bit more afterwards. So the coherence ones, the figure on the left is the coherence estimation routine, which is basically generating a coherence pair using GPU acceleration. And this is a very, I mean, you could recognize this if you're a common Snap user. So these boxes here are simply, each of them is a separate function in Snap as well. So we've been kind of trying to get the exact same results with our GPU-based approach. So these are the functions that we have implemented. And on the right is the coherence time series generation routine, which is essentially the same routine, but it has some sophisticated data handling mechanisms in order to really facilitate the usage of the generation of long time series. So you could have just 2 inputs or 10 inputs, even 20, 100. You could do that processing automatically. We also did accuracy assessment. We always do accuracy assessments against some, let's say, reference software implementation. So in this case, it was the Snap implementation. I think the version was something like 8. And the figure here depicts the kind of relative error in each pixel, but that's in, you could see that the relative error is in the order of around 10 to 100 pixels per million. So it's really small differences, quite insignificant. So the accuracy of our results compared to Snap is very, very high. For the calibration routine, this is a simpler one. Is essentially for generating calibrated geocoded Sentinel-1 products, and quite straightforward. Nothing too fancy, but also very fast. And this we've got even closer to the Snap implementation. So very few differences. Highly accurate. So on top of the algorithms, I'll tell you about the focusing ones afterwards. We offer some general functionality. So if you've all of the functions, all the routines are GPU enabled, GPU accelerated, and they work on NVIDIA GPUs because we use the CUDA technology. And based on which GPU you have, we make kind of smart use of it. So if you have those very sophisticated GPUs like the NVIDIA V100 and I think the H100 also, they provide capabilities of kind of partitioning the GPUs. So if you have sufficient GPU memory, you could even run multiple instances of the ALUS toolbox on your one GPU. So if you want to process like 100 images, you wouldn't need 100 GPUs to parallelize that. You could have maybe 10 or 20 GPUs in your cluster. You could still do it because multiple instances of the software could leverage a single GPU, so partitions of one GPU. Also, the inputs to the software, so the scenes, the inputs are supported on multiple levels, so you could provide the full Sentinel-1 scene, only one subswath, or you could also do the processing on burst level. But you could also, it also supports a user-defined, so an AOI-based, area of interest-based input in the shapefile format or just well-known text. And you could run it globally because the Copernicus DEM30 is also supported. So our approach has been on pure, so focusing on pure processing, getting the processing routines fast, very fast and reliable. So the software simply has a command line interface, which allows it to be integrated into an existing processing environment. All you need is a Linux environment, GPUs in your cluster, and the data made available. Any kind of analysis you would need to do in some other tool, which could be the Snap Toolbox or QGIS or whatever else. And we're also taking the approach that the auxiliary files would have to be provided in the processing environment. Of course, you could have simple means to download them, but we've been trying to have as few external dependencies as possible. Yes, and there are some, in our repository, there are some Docker images available that you could use. There's one also with the Jupyter Notebook as a front end. So if you use the Jupyter Notebooks and you don't like the command line interface that much, you could also try the software out with that. And here is an example how the input to the coherence routine looks like. So you just specify your reference scene, your secondary scene, the output directory for your results, and also the region of interest is a polygon, and the DEM files. Okay, also a bit about SAR focusing. So last year we had an ESA TDE activity called BULP, so the bulk processing via parallel computing. And within that project, together with our colleagues from SARMAP, we developed a prototype processor for ALOS pulsar zero Doppler focusing. And we achieved very high, very fast results. So the output was nearly interactive, took around less than 2 seconds to focus a full pulsar image. So this has huge potential to develop into a serious, real on-the-fly processor. It supports several modes. And you can see the output figures here and also the processing chain as such. I have a particular slide about the processing performance of this SAR focusing. So the total runtime of the focuser was around 1.7 seconds for one pulsar level 0 product, which is around 203 megapixels, so a quite large image. And the calculations on the GPU took around, what you can see there, like something like 0.3, 0.4 seconds. So a key message here is that we know that the processing on the GPU can be very fast, but it could also be the transfer transfer of the data to the GPUs from the CPUs could also be a bottleneck. In this case, we also did that very, very fast. So the end-to-end processing of one scene took 1.7 seconds. So for this case, I mean, if you need to really have a large reprocessing campaign or such, I mean, this kind of software really enables that. And now for some recent developments. So based on the success of this previous activity, we decided
you have
to
2 minutes.
To continue with SAR focusing. So as part of the ESA QA for EO service, we are now developing the NVISA ASAR and ERS SAR level 0 processors. And we have already some preliminary results. I mean, here's some graphical example, but the message is that the focusing can be done. It's on the order of magnitude. The speed is on the order of magnitude of the previous slide. So we could do that in less than 2 seconds. Process a full level 0 scene. So in the future, we could really have interactive processors that help access the users access heritage data. So very fast on-the-fly processing could be done, and also any reprocessing campaigns could become much faster. I mean, if you need to process 1 million scenes, if it takes less than a second to process one scene, that becomes reasonable. And again, I mean, this is also going to be open source. So here we have the open source SAR focusing tool that Marcus is willing to support in Snap. So just have to wait until next year. So the ALOS tools have been also put into quite meaningful use. So as part of the C-Scale Horizon 2020 activity, Guido Limon from the European Commission's JRC used our software to produce a year-long series of analysis-ready data, analysis-ready coherent state images over Ukraine to monitor agricultural activity during the Ukraine war. And he was using the CreoDias environment for that, and to generate the coherence pair, it took around 11 seconds per subswath on the GPUs, which is again very, very, very fast. And we are really proud of this use case because this shows that the software really can be put into meaningful and good use. Quick words about the potential opportunity. So this is just a concept that we've come up with. So if you can generate any products in milliseconds, then why would you store intermediate products at all? So we could do on-the-fly processing directly from raw data into whichever level needed, to level 1, level 2, level 3, and deliver it directly to the users. So you would save on storage costs, you would get very fast time to products, less overhead in processing, and you wouldn't need any reprocessing campaigns at all because you would generate the products always from level 0. We think that the GPU technology can make this really possible. So thank you very much for your attention, and I'm here until Wednesday, so any discussions, questions, I'm open to discuss.
Thank you very much, Martin. Any question?
Apologies if I missed this, but I'm assuming you're using like the range Doppler algorithm to focus this, like a frequency domain algorithm? Okay, cool. And what kind of GPUs were you using? The performance is really impressive, so just wondering.
We've been testing with different ones, mainly the NVIDIA ones, A100s, B100s, but also over time, not that advanced ones. So different grades, usually the ones you get in the common processing environments. I can't remember many models from the top of my head.
Okay, yeah, because running this on like a laptop with a smaller GPU, is that also possible?
It's
and
possible,
do you get similar processing times?
Yeah, you would be on the same order of magnitude, but probably not that extremely fast as with a really server-grade GPU.
Awesome, thank you.
One of the more computationally intensive parts of some processing is pixel offset tracking, the cross correlations. Are you including that in your GPU code?
No, we haven't worked on that. No.
There's another. Please use the microphone.
Yeah, that could be parallelized massively, no? Would you think?
That's a good idea for the future, yeah.
And perhaps a comment? Yeah. You should perhaps advertise also that the consumption of a GPU is less than the CPU. So...
You were saying, sorry?
The consumption of the GPU is generally less than the CPU.
Energy consumption, you mean?
The energy consumption,
So, per se, like what our experience is, I haven't done a very deep analysis, but if I remember correctly, the power consumption, that was in some article that was published. So the average power consumption of a GPU is around double of a similar CPU. However, if you could do your processing 10 times or 100 times faster on the GPU, the total power you'd be consuming is much less. Yeah. So yeah, definitely also from a power saving perspective, if you are doing very large processing campaigns, this becomes reasonable. Yeah. Okay, yeah.
Okay, so then it's time to move to the last speaker of the session, Pius Agram from Descartes Lab, and he's going to talk about GIS-based workflows for SAR/INSAR science data systems.
Hopefully I won't go too much over time here. So we are a data engineering company, which means we specialize in handling large volumes of data and high performance computing. Today I'm going to talk about SAR and SAR workflows that we've developed, and when I say GIS, I actually mean you're doing all the processing within a GIS framework and not doing it outside with the tool and then bringing it into a GIS software visualization. I'll also present some results from our applied science team who use the product that I'm going to talk about extensively. I'll describe our Sentinel-1 workflows in a GIS-based framework. I'm going to talk about how standard SAR and SAR applications are easily done within GIS. You don't need special software tools. Then I'm going to talk a little bit about multi-sensor, multimodal analytics, which is mixing Sentinel-1 with other sensors. And talk also about upcoming global SAR missions like NISAR, ROSEL. Having implemented global scale Sentinel-1 processing the traditional way that all the previous speakers spoke about, and having implemented it this way, I believe we really have to consider using the GIS approach for things to be cost efficient, energy efficient, and scalable going forward. There's also a lot of open small sat data coming out. I'm going to comment a little bit on what we are doing to prepare for processing that type of data within GIS frameworks as well. And in the end, I'm going to talk a little bit about what we can learn from other Earth observation data sets. We sort of tend to live in our own isolated world and not keep track of developments from other types of sensors. There's a lot to learn, and I think this geocoded SLC concept is something we should pursue more actively. This is a slide from FRINGE 2021, where we presented our global scale work on Sentinel-1. We routinely process 3 products out of Sentinel-1. SAR backscatter from all we transmit data, which is dual pole, single pole. This is on a 10-meter UTM grid. The UTM grid is compatible with Sentinel-2 from get-go, so you can overlay them on top of each other for mix and matching them. We do all interferograms less than temporal baseline of 24 days. And all these products are done on a burst-by-burst basis. We also do a product called RTC Factor, which we demoed in 2021. I'm going to come back to it a little later. We're going to talk about how radiometric terrain correction, you don't have to do it every image. It's really a waste of resource to recompute it for every image, incoming image. We use geocoded SLC bursts, which you heard before today. It's great. Opera is going to do that over North America. But this pipeline that I'm talking about has been operational for 2.5 years. Close it. Around the mic, yeah. So this pipeline has been running for 2.5 years. It's hands-off, it's automated, and we process all we transmit data globally. With the upcoming global missions, we expect, at least on our side, to have a similar suite of products. Whether the missions themselves generate it or we generate it is a question for us going forward. Just a brief overview on geocoded bursts. You all know Sentinel-1 SLCs are distributed in safe zip files with TIFF files, and each TIFF file has a certain number of bursts. For us, the processing unit is one burst. We don't need the entire zip file. We've built data access mechanisms where we can pull the one specific burst we want over the network in 5 or 6 seconds. Could be anywhere in the zip file. We've mapped all the bursts for Sentinel-1 already. And the processing, because we don't need the whole zip file, we don't need large disks. We could do the entire processing in the 3 GB and 1 CPU. So it's like super cheap for us to do global scale processing with this. Eventually, what we end up with, starting with the burst in traditional slant range coordinates, is this geocoded burst on a UTM grid that's 10 meter northing and 2.5 meter easting. We chose this first for compatibility with Sentinel-2, but also this has nice oversampling factors over the actual data resolution. So we're not introducing any artifacts by geocoding early in the processing pipeline. Once you have the geocoded bursts, then backscatter is absolute value of the complex number. Interferogram is cross multiplication of complex numbers. No, you can throw whatever filter you want. You don't like boxcar, you like Gaussian, you like some weird shaped filter, you pick, you can do whatever computation you want on the file. And all of these can be done within your standard QGIS, whatever GIS software you want. You don't need any special tools to do this. This is very similar to the geocoded SLCs that Howard Zepker proposed in 2017, but he proposed focusing the data directly onto a geocoded grid. If you're able to do that with all calibration accounted for, great. In this pipeline, we start with the calibrated SLCs and do the geocoding. Like I said, radiometric terrain correction. I refer to you to the paper that came out earlier this year. Radiometric terrain correction is essentially the process by which you account for difference in imaging geometry. That's essentially what you do in INSAR as well. They're the same operations. One is correcting amplitude and one is correcting phase. So they all are related to baselines. And we know Sentinel-1 has this narrow baseline tube. So it's same as INSAR processing. Pick a reference image, you compute the correction, and for Sentinel-1 specifically, since the baselines are small, that correction is more than sufficient for radiometric terrain correction of every incoming image, which means you have a stack of 400 images like somebody showed over Europe. You only need to compute this once. You don't need to expend resources 400 times to do this. You just compute this once, every incoming image, do a cheaper geocoding operation, and then add this correction factor on. You don't even have to add it on the fly. This is what people who work with Landsat and Sentinel-2 do. They do red, near infrared, and NDVI all the time. It's the same plumbing, same framework. It's band math. Since all our products are on the same 10-meter grid, nothing fancy. Simple math operations between these images are sufficient to do radiometric terrain correction. The other thing this enables, which was something that used to annoy me a lot personally, maybe not other people, is that the RTC folks have their set of tools, the INSAR folks have their set of tools, they don't talk to each other, they don't produce products on the same grid. There's no consistency between them. They want to do their own grand processing job, they want to do their own, but this sort of framework allows you to do all of that consistently and have good statistical properties. Having implemented all this in Sentinel-1, this is my personal recommendation that we don't really need GRD products. Using GRDs is way more expensive than SLCs. If you have the right data access mechanism to access individual bursts, you will end up reducing your processing costs by an order of magnitude, because you'll be using smaller computers, a lot less memory, a lot less disk space to produce the same set of outputs. So if GRD products can be eliminated and that budget can be used for something more useful, that would be awesome. That would be my personal recommendation. In the process of, if you go see the paper, we also noticed that we built unit tests, and Snap performance in radiometric terrain correction is not very good yet. We will definitely be revisiting this as newer versions of Snap come out, and we've described elaborate experiments on how you can actually test this out. We've also shown in the paper that this is not, this framework can go as far as like ALOS-1 baselines, which is 6 kilometers. So basically, any modern INSAR compatible mission, you get radiometric terrain correction for free if you make the right equation changes in a couple of places. So the common INSAR applications that I've encountered from users, I've seen on Snap user form, is basically they want a radar backscatter, they want INSAR coherence, and they want INSAR phase. And for us, since we process these products globally, accessing these and making a GIF out of it is like 3 lines of Python, just the way we build GIFs out of Landsat or Sentinel-2. These are sort of foundational products on which we build our analytics pipelines. Some of the examples of these are, we have something called quick look velocity or time series. How many of us have wasted times, like I want to do an elaborate stack processing and then find out this area is not really suitable for INSAR analysis. For us, we can arrive at this conclusion in like 5 minutes. We'll be able to run a quick look notebook over, say, a 5 kilometer by 5 kilometer, and then decide whether, oh, this is a hotspot, whether it's worth investing all this processing time into generating this computationally intensive stack. We had a summer intern this summer, Rebecca from University of Texas Austin, who built it, who basically took our quick look notebooks and made a simple Python interface that you run in a notebook. You just give it a lat-long, a kilometer size, and start date and end date, and say whether you want velocity or time series, and anywhere in the world you'll have analysis spit out in 10, 15 minutes, because we have the global interferograms less than 24 days globally. We also do full resolution infrastructure monitoring. Okay. So we also do full resolution infrastructure monitoring with Sentinel-1. In this case, the reason I'm pointing this out is for full scale resolution, you need the data to be complex valued. So in the previous case, we were deriving the quick look stuff from real valued coherence, real valued phase. Here, it's complex valued data, but the data we access the same way. Like you give a box, you give a UTM limit, and it pulls out pixels, and you have your complex image, you cross multiply and do your time series with it. We call this geocoded SLC. GSLC is the abbreviation we use. We've also done this with other sensor data, like TerraSAR-X and Cosmos SkyMed, over limited AOIs where we could get some samples to play with. But this is this powers our infrastructure monitoring anywhere. Since we operate on bursts, if you come to us and say, I want to monitor all volcanoes, first of all, we already watch it with our global product. And second, if you want the all bursts following monitoring all volcanoes, it's like 400 bursts, 500 bursts. It's really straightforward to scale up the processing. Or you have 200 mines you want monitored. It's really easy for us to just scale up the processing at that level. The other thing I want to talk about, especially since I was talking about GIS, is the multimodal analytics. I'm using one example here of deforestation, but the same applies to, say, agriculture, generic change detection, surface water. Deformation analysis is pretty much the only application where Sentinel-1 data is used by itself. In every other application that done by our applied science team or our customers, they're always mixing data from multiple sources. Sentinel-1 is not the only source of data they're going to use to make decisions. So if you're going to build your data system focused only on SAR, you're going to hit a roadblock at some point of time. In this case, we're using Sentinel-2, NDVI, Sentinel-1 backscatter, and Sentinel-1 coherence. And you see all of them have this nice signal around the deforestation event. This is elaborate analysis done by our applied science team for a couple of validation sites, where they did analysis purely with optical data, purely with SAR data, and then mixing SAR and optical. We're doing, this is the simplest example I could find. Think also that Landsat is used extensively in this. So there's actually more sensors typically. Clearly, SAR coherence plus backscatter plus optical is what makes the most number of reliable detections, not just optical, not just SAR. And just extrapolate this, and this observation is consistent for agriculture change detection applications at our end. So based on what I've described or what we've built for Sentinel-1, how are we preparing for the upcoming missions? NISAR, ALOS 4, Roselle, they're all designed to, I hope I got the ALOS number right. They're all designed for persistent INSAR analysis. Backscatter is okay, it's easy. It's probably the easiest application you can do with SAR, but it's not the only application. Coherent change detection has proven to be really important based on feedback from our applied science team. Phase measurement for deformation is another useful component. Though L-band gets noisy, but still, it's going to be a useful component. From our point of view, what we expect from these missions is, at a minimum, access to calibrated high-quality SLCs. I would say GRDs are not worth it. That is our feedback. And when I say quality, it's not just imagery. It's the quality of the metadata. It's like, how good are the orbits? How good are the timing corrections? How good can I geolocate it out of the box readily? That's what I'm talking about when I say quality. SLCs support both backscatter and interferometric applications. In general, having worked with a lot of SAR data and Sentinel-1, Sentinel-1 has raised the bar on what is the minimum acceptable level. Every new global mission that comes out, I think, will be compared against Sentinel-1 for ease of automation. So if you are operating in a burst-based mode, I strongly believe you should support data organization and direct access to these bursts. That should be the minimum requirement going forward. If you are not a burst-based system, you should use a clearly defined track frame system to enable automation. The volumes of data that we're talking about from these missions are so huge that a human operator cannot keep up. So you really have to think about how you're going to automate all this processing. We are really excited on the analytics side for the coherence and backscatter at C-band and L-band being available at the same time in about a year from now. So on the analytics side, we are preparing for that as well. There's also a lot of sub-meter resolution SAR data coming out. Capella, Umbra, ISI. Our experience working with this is for automation, you really need improved DEMs at a global scale before you can automate processing these. Right now, you can sort of automate some processing. You can go get LiDAR DEMs over select areas. But if someone sends you a high-res image to you, you actually have to expend quite a lot of effort getting a reliable high-res DEM. So I think the first step before operationalizing, automating this sub-meter SAR space is we need 3-meter or 5-meter DEMs globally. Reliable, high-quality DEMs globally. Till then, there's always going to be a human in the loop. There'll be human. You can only automate it to a limited extent. The other challenge is these small satellites so far, we've had to deal with a fairly large diversity in imaging geometries and modes. It's not like Sentinel-1 with a narrow orbital tube. You're often asking yourself, is what I'm seeing real? Is it change that happened on the ground, or did it change due to the imaging geometry just because you happen to be looking at the ground from a different perspective? So far, at least currently today, often requires manual intervention in the interpretation stage. So hopefully, if possible, if their imaging geometries and modes stabilize, that will help automation in the analytics side. We've also sort of automated some standard applications. Here's a standard motion detection moving target indication analysis from a single SLC. Once you geocode an SLC, you can't go do subaperture analysis. So what we do is you create the subapertures and just save it as 10 bands of an image. It's like Landsat, but each band of the image is a different subaperture, and then you can automate it and color it. And there are some applications you could do fairly out of the box, but when you have more than one image involved, you'll have to actually have a human right now for interpretation. In working with our applied science team and talking to our customers, there's a lot that we in the SAR world can learn from the rest of the Earth observation space. We are a big part of the Earth observation solution. Everyone believes that, but everyone's also clear that we are not the only solution. Interoperability with the other Earth observation data sets is very important. I find it easier to communicate SAR data characteristics with our applied scientists by bringing it early into the GIS framework. I think it'll lead to broader adoption. part of the reason why we started with Sentinel-1 grids that are compatible with Sentinel-2 from the get-go. The other thing we tend to do a lot is like we overemphasize the need for specialized tools for SAR. You don't really need to overemphasize it. For all practical purposes, SAR processing, the SLC you get is in its custom projection system, and you use a very specialized custom interpolator. So you could say it's a GDAL1. It's not really much more fancier than that. So we need to start training people to think about SAR data that way, rather than we throw them into the deep end with like, here's a software you need to do, here's the input files, here's the output files, without really wanting to delve into the internals of the software. The Earth observation community is very comfortable with map projections. There are plenty of sensors out there that use weird map projections. SMAP, GOES, MODIS. They have no problem with that. And it's part of the communication. You communicate to them that what you have is a weird map projection, they get it. I think that's another sort of eases the barrier to entry. And one thing we could really do, which I hear again and again, is coalesce around a usable level 2 product. For most Earth observation data sets, number of level 2, level 3 products is significantly greater than level 1 products. We don't have a standardized level 2 product in the SAR world. A large majority of the users just do the same standard processing themselves again and again. So hence the work from JPL folks on geocoded SLCs, I think is a good start, and I think we as a community should start thinking about coalescing around a geocoded SLC as a proper level 2 product. Supports backscatter analysis. User can go do multi-look themselves as much as they want. Supports INSAR, again, as much multi-look and filtering as you want. Keeps manipulation operations simple, very GIS friendly. We have also shown that the standard RTC correction is nothing but band math in GIS frameworks. So that is not a hindrance. You get to preserve resolution in a GSLC product. Also for a lot of the sensors, like the small sat sensors, where each image has its own resolution, you get this intermediate level where you get to standardize the product. You could have whatever resolution at the original L1 SLC, but you could say my GSLC is always going to be 1 meter. Makes life easier for the end users to work with. And the other big takeaway for us, at least, is the scalability and simplicity of the maintenance of these workflows. The processing costs go down by an order of magnitude. If ALOS 2 had put out burst-based products, I bet our processing costs for doing ALOS 2 would have been 2 orders of magnitude lower. So there's a lot to be thought about in terms of how data is distributed and how level 2 products can be built from level 1 SLCs, which people find hard to navigate. The one important con is this makes requirements on the data quality from the providers more stringent. The quality of the metadata has to be high, quality of the imagery has to be high for all these workflows to work this easily within GIS frameworks. That's all I have. I've included reference to our previous talks in the last slide as well.
Okay, so we have time for a couple of questions.
Thank you very much for your presentation. It's super exciting. I have just a technical question, and because I like very much this idea of geocode SLC, but when you geocode, what you really obtain is and you process to obtain coherence with the geocode, you have no longer a constant number of looks when you process.
That is correct.
I mean, I know that this is a technicality, but have you figured out a way to try to solve that issue? To assure that when, I don't know, you make a box plot, boxcar of 5 by 5, you obtain 25 equivalent constant number of looks, which is for some statistical analysis, for instance, for classification, it's necessary, and you eliminate this additional variable on the data.
I completely understand. I think our solution to the problem was we switched the product under the hood, and the customer didn't notice it.
Repeat again, sorry.
Our answer to this was we did a test where we switched the product under the hood. One process traditionally and one process this. And the customer really didn't notice it. So I think this claim that this is a problem, I understand it's a problem mathematically.
Yeah.
I think we need to do that comparison rigorously to show that it is a problem.
When you filter many looks,
exactly.
it's no longer a problem.
I
accept.
From my experience, people really didn't worry about it when they looked at the new problem.
Yeah, but when you want to analyze, want to make some accurate statistical analysis for PDF description, and if you want such amount of data to I don't know, to make kind of a big data analysis of statistics. I mean, at least I think this...
I completely agree with you. This is what I would call a standard trade-off question.
Yeah.
How much error am I incurring more? And I suspect that number is going to be smaller than to worry about.
Okay, thank you very much.
It's a trade-off study that needs to be done.
Thank you very much.
Thank you for your talk. It's really great. I just want to ask that you plan to generate 5 to 10 meters global DM, or what kind of satellite data you want to use?
Oh, no, we're not planning to generate the DEM. I'm saying that is a prerequisite that the whole community should think about. Like, we won't get to operationalizing use of sub-meter data till we actually have a 5-meter global DEM to get there. I don't know how we are going to get there, but if someone claims they're going to do global Umbra processing or Capella processing, I'm going to be very skeptical. Because I think to get there, the first step is to get to a reliable 5-meter global DEM first.
Oh, thank you very much.
Excellent presentation. What do you think is preventing us from doing the reforms? What are the concrete actions we should take to fix the?
My answer is we train people with what we're familiar with. All the tools that are out there, Snap, ICE, GMT-SAR. Remember, these all came from ERS and NVSAT era things. And Sentinel-1 metadata quality is what is enabling this. If I go try to do this in ERS and NVSAT, I'll still have to estimate a constant offset by doing cross-correlation and things. I think SAR sensors have improved, and I think that is what's enabling us to consider different methodology. We are still using the tools that were built for ERS and NVSAT. I think it's time to update or think about the processing paradigm a little differently.
Okay, last question.
When you make the geocoded SLCs with L-band data, do you do any ionospheric corrections?
We don't do anything. That's why it's a challenge for NISAR and all the L-band missions that I mentioned. I believe it should be similar to the ETAD corrections, that these expected range corrections should be provided with the data for this sort of mechanism to work.
Thanks.
Okay, thank you very much. Thank you to all the speakers. Marcus, you want to talk about the roundtable?
Yes, so to start the roundtable discussion, 1 minute, I'll get Nuno Miranda from the next room. I hope that the seed questions are on the drive. So. seed questions, this is not a comprehensive one, so if you have other questions to propose, please feel free. The first one is a generic one that is on the template for what does the community, and this community in particular, recommend that ESA will do in the short and medium term. So I've heard recommendations before for geocoded SLCs. I think it's a good one. Some people might disagree with that. So does anyone want to have a word? Any comments?
Oh, okay. From my point of view, I mean, with respect to the first question, of course, I mean, is to have access to the data, but also useful data, okay? I mean, to coherencies and everything. I won't give any recommendation into that. But one thing that would be very useful is to have, I mean, this is an old question, to have common data sets. I mean, the possibility to combine, I don't know, SAOCOM with ALOS, with Sentinel-1. I mean, I know this is very difficult to put everything together in one test site. And the other problem is to have ground truth for the data. I mean, if you are interested into some kind of applications, I mean, I think it's a huge amount of work, but it's worth to push into that direction, to have common data sets on the same area. Co-register is possible, I mean, at to some point, okay? So that would increase the possibility to extract information.
So you're suggesting that ESA should make a platform or some kind of processing.
I don't know how to
call it, where all this data would be available.
I don't know how to crystallize this, but the idea is to have common data sets. Okay, for instance, we have the Syncomap or other projects that we will present it in here with other data sets to have common data sets from different missions. I mean, because I think more or less we have a right to the limit with single technologies, single systems. So there is much more you can do with multiple combination fusion and these kind of things, okay? So, I mean, of course, you need these data sets for every single system, for wherever, but to make the effort to combine them or to have common data sets, I think it's worth the effort.
Right, yes. I mean, that sounds like that you are proposing some kind of a test site-based approach, because globally that gets quite expensive. I don't know.
Yeah, I know. Yeah, I know. But it is, at the end, it's worth to do. I mean, in the future, we will have Sentinel-1 Roselle, so we need some data sets. At the moment, they are quite limited, so it's complex. But I think the only ones that can make that are space agencies.
Okay, thank you, Carlos. There's a mute button.
Let me just comment on that. There are already some attempts to that, Carlos. You know that it was also one of the things that we discussed in Polinsar. And there are already attempts in various sites. So, for example, for agriculture or for ice, no? It's not still, let's say, a common platform or point where you could refer. After Polinsar, in fact, we started to collect all of this information from different projects and to see how we can combine it. So this is something that hopefully soon will be available for the community. But yeah, this is for sure something that everyone would appreciate.
There is another option between GSLC and Coreg SLC because here you're duplicating data volume between the L1 SLC. And for good co-registration, at least in C-band, if you are estimating correction parameters, constant range offset, constant timing offset, or some representation, if the space agency takes on the job of only estimating these correction factors, the user can generate the GSLC or the Coreg SLC with those and the original SLC. And these factors you compute once, they hardly take a few kilobytes because it's met in. So that is another option where you provide a correction service to enable co-registration, but not actually recreate the whole product suite.
My question is more dedicated to the PS-INSAR tool. As we'll follow the stamps line, or we'll try to have own software, dedicated software for PS-INSAR. Because we use stamps, we use that workflow that is from Snap to stamps, but I miss the opportunity to join ascending and descending orbits, and different data sets that is possible in different softwares, but not in stamps. So as we'll follow that line, or we try to have some independent tool?
Well, I mean, to me that sounds like that the community should step up and make such an open source tool, then those could be supported. I don't know if you're familiar with Pyrate. Personally, I'm not very familiar with it, but it's a fully open source, Python-based Australian software that does SBAS. But I mean, we specifically with Snap, we don't want to solve all the problems because there are too many problems. So that's why we facilitate communication with other tools, and then there are other communities that can then help you with stamps, for example. So my view is that ESA should not go into the PSI business. There's a lot of companies already doing that. But maybe, I don't know, if you, who's developing stamps? It's an, oh, there's a comment over there.
I have a comment about stamps. The last time we made a commit to it was in 2015. And so it's amazing to see so many people still using it. So related to that question, actually, is I have 3 points to make. A few years ago, from the comic community here in Leeds, actually, and wider UK, we released a statement to try and encourage people to move away from the master and slave terminology. And it's, again, amazing to hear that people are still using it. And I think that's a legacy of stamps, because we haven't gone back to do control find, control change in stamps, because none of us have the time. So please encourage people to move away from that terminology. Most of the software have, ICE and GMCR others. It is literally a matter of control, find, replace. And we can do that very easily, please. Second is, again, a legacy of stamps. Originally, the way it was written is this, what originally was called single master approach. Oh, gosh. That wasn't me. This single reference approach. I mean, the Sentinel-1 time series is only getting, and some of these baselines can be at 5 years at least.
Can we switch the microphone?
Let's try.
Okay, so I'll just stand and shout. So, we all know the issues of temporal decorrelation. So it blows my mind that we are still using single reference interferometry. We ought to be moving away from that, particularly because the longer these time series get, the worse your results are going to be. And the third point was around Pyrate. Pyrate's even older than stamps. Really? So it developed again in Leeds before even stamps was thought of. So again, from from MATLAB, which was then updated into Python recently by the Australian folks. So I think it's probably time we sort of develop more novel, more up-to-date time series methodologies.
Eric has a question here or comment?
Yeah, MinPy also works with the MinPy software. The MinPy software is a Python open source package that works well with Snap. So that's and that's being actively maintained. So that's a good alternative.
So would you recommend that we support MinPy from the Snap side? Is that needed?
I think it's very easy to put the Snap output into MinPy. It's just a matter of organizing the directories with a certain structure. So I think it would be very easy it wouldn't require much work.
Okay.
Thank you for a very interesting session. You're asking recommendations, then if I may, then it's just one recommendation. Try to get the geocoded. It's working now. Okay, let's hope it's stable. Try to get. I will just say, drop the microphone. Just try, if possible, try to get the standard adapted as soon as you can at the first test products out. It always will be compromised. There always will be some users not happy. It's moving away from the native radar geometry and so on and so on. But eventually it will be an iterative process anyways. So even if it's imperfect at first, like the sooner you get the first standard adapted and first test products out, the sooner we get the ball rolling and the things going. Because inspired from the last presentation, I think it would really make a big impact of going out from the sandbox of the SAR community.
Thank you for the comment. I personally agree, but what the ESA's plans are, for Rosell, I believe the geocoded SLC is a standard product. And for Sentinel-1 next generation, I don't remember. I will have to check. There's a session tomorrow morning on future ESA missions. Tomorrow morning.
Thank you.
Yeah, Lynn.
I can shout. This I can. It's a comment regarding the second point, more of an end-user perspective. So about the need of harmonizing interfaces for access to different different platforms. And I believe it's not really realistic to have similar interface at different level, because I use not the same at the regional, national, or European level, and the data are not designed the same way. But something that could be valuable would be to really have from EDNS to present a direct link to the national services, even when in the web JS2 if possible, to for example, use Zoom on the country, and the user can see, get a message saying, note that there is also a national service with different kind of projects, higher resolution, and such. I don't know if it's all possible. Really nice.
Thank you for your comment. Any other comments? The floor is really yours. We don't have to stick with these 4 questions, but so anything related to, there was a talk about GPUs, anything GPU related, that any recommendations to the community, to ESA?
This one there. Carlos?
I would like to make a comment on these GPUs, as you mentioned. I mean, it's more my comment is more general. It's about hardware, and it's something we are facing in Catalonia, for instance, is that you have a large need to have much powerful machines. And for some people, this is restricting the access to process the data. For instance, this is happening also in the world of data science. Only few companies in the world have the resources to process the data. So this is really, and it's becoming an entry barrier, especially for research groups, for institutions, for small institutions. So we have to be careful about that. We have to provide also that, for instance, in Catalonia, the government is trying to push to have a machine for all the companies, because a single spin-off cannot afford for that. So this is becoming, in this era where we are going to global applications and global processing, this is going to become an entry barrier for many actors. So we have to be careful of that. Also the storage, okay, because we are growing. And I mean, I'm from the university world, so I have my problems, but for spin-off companies, this is going to become for many small companies, this is going to become an entry barrier. In the same way of language models in artificial intelligence, okay? It's the same way. So we have, ESA should take care of that needs too. Thank you.
Yeah, we're going to capture that. Carlos, thank you. Maybe the microphone works. Let's try.
Yeah, when we are submitting projects, we are more and more, we have more and more pressure to mention the cost of energy, of CO2 pollution when we produce our research, and it's rather hard to get the information on how much it costs to produce this data, and all these data are generated to observe the Earth or environment things. So one thing that could be perhaps good is to have an estimate by the ESA itself of how much it costs to launch the satellite, to generate the data, so that we can estimate our personal cost of research.
Right, so if I understood you correctly, you would want some kind of, because people do different processing using different software and different GPUs, CPUs.
Say, when I get my data,
yeah.
What was the cost of having this data?
You mean the total cost of satellite launchers?
Yeah, for example.
That's not very easy to calculate, but yeah.
Yeah, but the astronomy community has done the job.
Yeah.
Yeah, and for example, the launch is not the higher cost. It's preferring the thing before. So that's the attempt. It's not easy to do, but it's worth wondering.
No, I mean, of course the budgets are fully known. What's the Copernicus program has cost, so it's not an impossible figure to calculate, but there are several figures. So yeah, let's put it in the recommendations that this could be something to be looked at. But you want, as a taxpayer, you would like to know already before you download your product that how much.
Yeah, or at least have an insight of what's the cost of
yes.
Having this data.
I don't think there's anybody here in this room from a small SAR provider, because they might have an actual number that they could quote if it's not a secret. So how much is the cost per image for a small mission? So okay. I think we are close at the allotted time, so unless there are any last comments or anything else to add, I think we should join the welcome cocktail sponsored by the UK Space Agency. I think it's starting now.
Thank you.